Thank you very much, and it's a great pleasure to be here today with you. So I'm going to talk about AI for engineering, which is a little bit different from the typical uses of AI. So we are basically looking at how we can apply AI to electrical engineering, manufacturing, civil engineering, and healthcare engineering. And one of the reasons we are doing that is that in many of these, engineering domains, there are an increasing number of issues that will benefit a lot from AI technology. And they come from scalability issues in large supply chains, the need to model and mitigate risk in many different application areas. There are also a wide variety of applications now in engineering that require real-time constraints, and they impose some computational requirements, obviously, on the optimization algorithm that have been used. And with the scale, it becomes challenging to satisfy these real-time constraints. There is also an increasing need of including fairness and equity in many of these engineering applications. And finally, and I will talk a little bit about that at the end, there is also a need for a next generation, a set of next generation design tools, especially for manufacturing. So all these applications, in a sense, are meeting the limits of optimization technology. And this is where these combinations of machine learning and optimization can play an interesting role. And what I'm going to try to do today is to show you the potential of combining these two technologies and various ways of actually making them collaborate. Now, the challenges that you have in engineering is that you typically have a number of constraints, physical constraints coming from physics, obviously, and also engineering constraints not to damage equipments and things like this. You have also business constraints in many of them that are imposed on you and that you need to satisfy. And finally, in some of the applications that I will show you today, the inputs of the machine learning problems are gigantic. They can have millions of inputs. And I will show you some examples of that later on as well. So I'm going to talk about 4 topics today: optimization proxies, learning to optimize, end-to-end learning, which is also known as decision-focused learning or smart, predict, and optimize, and then very quickly about learning inverse optimizations. So I have a lot of topics, so I'll go fast in many aspects of this talk, but I hope you will have the opportunity to ask some questions at the end. So let me talk about optimization proxies first. And the idea in optimization proxies is to learn the mapping, essentially the mapping of an optimization problem from input to output. This is a nice set of machine learning problems because we have the ground truth, which is very nice. So there is the data is essentially clean. So I'm going to illustrate that on Power System. Power System is the largest machine on Earth. Just in the United States, it braces about $400 billion in electricity. And as you know, we are capable of doing this talk because it works. We almost have electricity all the time. It's a very reliable system. It's a huge success story for optimization, although most of the public doesn't even know that optimization is being used, as well as forecasting and machine learning techniques. This is, for instance, a project that we have with MISO, the independent system operator, which basically run a power system going from Canada to New Orleans. And it serves about 40 million customers. And currently, it has only 17% of renewable, mostly, a big share of gas and coal power plants. One of the interesting things about these systems is that they have a variety of forecasting and optimization problem. This is how these markets are organized. So the day before, you are deciding which generators are going to be ready for generating electricity. This is called a commitment. And then every 15 minutes, you're looking at adapting this commitment because you may not have enough at that particular point in time. And then you have the real-time markets, which is trying to match the load, the demand, and the generation. So this is the pipeline that we have built here in my lab, which is essentially a digital twin of what MISO is doing. So we start from the offers the day before, and we make this commitment generation decision, which generators are going to generate data are going to generate power. And then this is during the day of operation. You have the FRAC, which is essentially taking the forecast now and adjusting these decisions and the lag that I mentioned before and the real-time market. So we have this very interesting digital twin now that we can experiment with, and I'll talk about some of these things. So this is an illustration of this digital twin of the French system. I can't show you the MISO system for security reason. This is actually, also not the real French system. We had to move the generators to not show you where they are actually located. But you can see how fast, this particular commitments of the generator and the generation is changing. This is the 15 minutes level. They change obviously every 15 minutes. The left is the energy. The right is the reserve that you procure to make sure that you don't you can deal with contingencies. And this is the real-time market, which changes every 5 minutes. So at the core of these systems, you have what is called the AC optimal power flow, which has two sets of constraints. The first one that you see there are the engineering constraints. The second one that you see here are the physical constraints. And I won't enter into the detail. It's not really important, but this is a nonlinear, non-convex optimization problems where the objective function is typically quadratic or a piecewise linear function approximating that quadratic function. So you're going to say, we are talking about power system. You just told us that it works. So why are you talking about this? And the reason, obviously, is because we are trying to push the amount, the share of renewables in this system. And MISO, for instance, has a target of about 32% in the next 9 years. And in general, we'd like to push them way above 50%. And when you start doing that, you have also to integrate the fact that the load is also much less predictable because of electric cars and also solar roof panels on top of the houses. And so when you do that, you increase the stochasticity of the problem. You increase there is a lot more volatility. And the prediction errors that you see there are also much more substantial. They have grown by an order of magnitude in the last 10 years at MISO, for instance. But this is also a great opportunity to machine learning because these networks are evolving very slowly. The physical infrastructure doesn't change. And therefore you can think that we are solving, very many similar problems all the time. This is what, Andrea Lodi calls the structure hypothesis. We are solving the same problems all the time with different instances. And this is what we can exploit. And so the challenge, obviously, is these physical and engineering constraints. So we're really doing empirical risk minimization under constraints here. So let me start telling you how we solve these problems using machine learning. And what you're going to see is a couple of insights from optimization that we are bringing into the machine learning space. And the first one is Lagrangian duality. And so the key idea is that this optimization proxy is capturing the input-output relationship for the optimization problem. And the architecture that we are really using now is something where you have an machine learning problem which predicts what the output can be. But obviously, they are not going to be completely satisfying all the constraints. That's not possible. But you have a second step here, which is feasibility restoration. And then you get the output. No, but even inside, one of the things that I will show you is that even inside the machine learning algorithm, we are going to introduce the constraints of the system. So this is once again the optimal power flow. The input is essentially the net load at every one of the buses. So what is the real and reactive power that you need to supply? And then what you see there is the output, the set points of the generators. That's what you need to produce. And these are the two things that you give to the generator: how much active power and what is the voltage magnitude set point. And so there have been a lot of papers in the last couple of years. This is a field which is moving rapidly in the power system area. And I'm going to summarize many of these results in a sense. So the input data is that you have a lot of these, load that you have to satisfy, and also what are the generator set point. And you can view this problem as an empirical minimization where you minimize the loss in prediction of these set points, and then you have to satisfy these constraints. And so you can start with a vanilla deep learning system. And once again, this is something that I will show you. This is a common topic in this talk. You will see that we are trying to adapt the machine learning algorithm to the structure of the problem that we are solving. And here we are predicting the voltage magnitude and the real power. But obviously, if you do that, you can actually get reasonable precision, but you don't satisfy necessarily the constraints of the problem. And it may be difficult to recover a feasible solution. So what we do is we do a Lagrangian relaxation here, and we use the concept of violations of the constraints to actually do this Lagrangian relaxation. So it's not a traditional relaxation, but it's very close to it. And so once you do that, you have to expand the scope of your network. You have to predict a lot of different set of values that allows you to actually represent the physical constraints, Ohm's law and Kirchhoff's law in this particular case. And so now you have this network, and you can extend also the loss functions such that you not only minimize the value that you are interested to predict, but also the auxiliary variables that you have to predict, and then the violations of the constraint, which are weighted by some multipliers. That's what you are trying to minimize. Now, the problem that you have here is that you have to find out, hey, what are the multipliers that you have to use? And this is where you can get some interesting insight from optimization technology. So the concept of Lagrangian duality is very well known. So what you typically do is that you know how to solve a particular optimization problem for a set of multipliers. And then what you try to do is solve the Lagrangian dual, which typically give you the best relaxation. And that's finding out the maximum value of the lambdas for this particular subproblem. So you find essentially, so in optimization technology, what you would do is finding the lambdas that are maximizing the lower bounds. And we do exactly the same thing here in the context of machine learning. So you, in a sense, try to satisfy the constraint as best as you can. The way you do that in practice is that you can have a primal step where you do the optimization on the learning here for a specific set of weights. And then afterwards, you are basically adjusting these weights using the violation of the solutions that you have at that particular point in time. And so that gives you the first step, which is the prediction. And now you have to recover a feasible solution. So what we typically do there is we use an optimization problem, which take those predictions and try to restore feasibility as best as, as quickly as possible and as precisely as possible. And the ideal things that you would like to do in general is a projection method. So you want to find the feasible solution, which is as close as possible to your prediction, because you, in a sense, trust your prediction. But you have all these physical constraints now that you have to satisfy. Now, this looks good on paper and it's very elegant, but in practice, this may be extremely difficult, especially in the context of this optimization, this power system optimization, because the problem is nonlinear and you don't have a feasible solution, obviously, to start it from. So all the interior point methods, in a sense, typically many of the interior point methods at least need a particular feasible solution to start, and you don't have one. So these problems may be actually as difficult as the original problem. And so in general, what we try to do is to say, hey, but is there a way to exploit the structure of the problem when you are doing feasibility restoration? And in power system, you have this concept of power flow, which basically takes this prediction and then solve a system of equations for actually recovering a feasible solution or an almost feasible solution. And the way this works, I won't go into the detail, it's classifying the various buses in different categories and then restoring the feasibility of the physical constraints. So let me show you some interesting experimental results there. They are basically comparing the vanilla network with the network with the vanilla neural net with the Lagrangian dual neural net, and then a neural net which use fixed weights for the Lagrangian multipliers. And so this is what you see here. So you see that obviously the Lagrangian dual problem is converging much more nicely, especially for the active flows, which are critical for feasibility of the constraints. And also one of the things that you see here is that when you look, if you fix the multiplier to a specific value, typically the accuracy is not that good. And so it converges very quickly to a local minima, which is very, doesn't satisfy these constraints in a very nice fashion and doesn't get the precision that you want. So it's really important to use these dual steps and this Lagrangian duality. This is an interesting slide as well, because it shows you how accurate these networks are. So the generators here are ordered from left to right. And this is the production of every one of these generators. So they are ordered left to right by the amount of productions that they have. So this is this y-axis on the right. On the left axis, you see the prediction error that you do. And what you can see here is that the order of magnitude of this error is about, the scale of this error is about 4 orders of magnitude smaller than what you are actually generating. So the errors that you see here are really, really very, very small. So this is an interesting slide which tells you what happens when you're actually restoring feasibility. How much do you move from the objective of the prediction? And you can see that the distance here is extremely small, and therefore you're really, really close to that particular objective, and you are well behind, well below the tolerance of what these algorithms are typically used when you do market clearing. So it's the tolerance of the optimization solver. So these methods here are really practical in the sense that they give you the accuracy that typically the markets need. Now, this is the time that it takes to train this network and the time that it takes to actually run the OPF. And one of the things which is a little bit worrying here is that when you get to this network here, they start to take a lot of training times. And what I want to do next is to show you another idea from optimization theory that can actually speed up that learning time tremendously. And this is this idea of Lagrangian decomposition. So what do we do in Lagrangian decomposition? Typically, we try to separate the problems into independent subproblems by relaxing some of the constraints, let's say the coupling constraints, and also putting them in the objective function. And this is what we would like to do here in the context of machine learning as well. We'd like to learn this subsystem independently of the other ones, and that obviously depends on the coupling flows. Now, one of the difficulties when you do machine learning here is that you may have the coupling flows when you are training, but at prediction times you don't have them, and so this is an issue here. And so the way we address that issue is essentially by having a two-step approach. The first thing that we do is that we learn the value on these coupling flows. And as soon as you do that, all the sub-problems are completely independent, and now you can learn them independently from each other. So that's the key idea here. Learn the coupling flows, separate the problems, and learn the regional subsystems in a sense. And so I want to illustrate that on what we can do on the French system and the French system plus a part of the European network. And what you can see is that these networks have about 10,000 or more links, but the coupling flows for the different regions in France, for instance, and in Europe are really small. You have about 300 or 400 different lines. So you can predict these lines, and then you can basically separate all the regions and have very small learning problems to try to learn. And the benefits of this is actually pretty interesting. So what you see here in blue is the prediction using the Lagrangian decomposition. And the black lines is the Lagrangian duals that you've seen before. And one of the beautiful things here is that you can see that this Lagrangian decomposition is allowed to model the nonlinear aspect of these generators here in a much more precise fashion. The ground truth is in red behind the blue curve. You sometimes see it, exceeding the blue lines, but it's extremely close. And in this particular case, it's almost always behind the blue lines. So what you get is two things here. In mid-sized network, you get an order of magnitude improvement in accuracy. And on large data set, you essentially can actually predict them with very high accuracy. So you have a nice way of scaling to large network using this idea of Lagrangian decomposition. And once again, you can restore feasibility and a very small optimality gap at the end. So this all look good. But what I've been working so far on these examples is actually something which is kind of an academic setting, because in practice, nobody really solved this very pure ACOPF problem. When you look at what MISO is doing, it's a lot more complicated. First, MISO is not only optimizing dispatch, they are optimizing energy and reserve, the reverse being there for dealing with contingencies. They are also using a DC model, but with line loss and a lot of ramping constraints to take into account how the generators can move up and down. They also take care of generators contingencies. So what happens if a generator fails? Can you actually accommodate the rest of the load using the load using the remaining generators? And then they have various kinds of zonal requirements for the various reserve. So the problem, it gets a lot more complicated, and that's what I was alluding to in the beginning of the talk. So you not only have all the inputs of the OPF, but now you have the commitments of the generators, you have the ramping constraints, you have the reserve requirements, and so on. And there are at least three different types of reserve that you have to accommodate. So if you take something like this is around 10,000 to 100,000 inputs. And then if you do multi-stage like in the LAC, you have about 1 million inputs for these particular problems. And obviously the output is still the same. It's how much active powers and now also reserve dispatch that you have to have for every one of the generators. So the problems become very, very big. And then obviously you have also to deal with the fact that they are renewable in there, and therefore they are not completely, the load is somewhat more difficult, the net load is somewhat more difficult to predict. And then you have this very bad news that I'm putting you on the screen here. And this very bad news is actually telling you that on a particular day, most of the commitments at different times of the day are actually different. So you are committing different generators at different times of the day, which means that the machine learning problems is kind of a mixed, problems where they are input integer variables. And then there is a regression once these integer variables are fixed. So it's kind of an annoying problem. Because of that, because now you have to learn, various commitments which are completely different at different times of the day, and they may be very unrelated. There is a good news, however, which is the fact that since this is a market clearing algorithm, you try to minimize cost, and therefore you can see that some of the many generators are actually 20% of them are at the maximum and 40% are at the minimum. And so really those, should be easier to predict. The other ones are the one that you adjust, around the day for the dispatch. And so that's a good news, because in a sense, you reduce somewhat the dimensionality of the problem. So this is a little bit, the input size that you have. This, G is the size of, is the number of generator, L is the load, and B is the set of lines. So you have very large inputs here. And the way we are actually doing this machine learning problem is by using an approach which classify and then predict. So the first thing that we do is we try to guess which predict, which generators are at the upper bound or lower bound. And then the next thing we do is doing regression. And inside the regression, we have a residual network, actually a specific type of residual network, which is called latent intervention networks, which also disconnect part of the network based on the commitments of the generators. But still, even though you are decoupling these two things and you're doing this residual network, you still have a very complex problem to solve. And so the way we address that complexity is by saying, well, instead of solving a huge, machine learning problem for the entire day and use the same model for every one of the periods, now what we're going to do is actually learn smaller model for every one of the hours of the day. And when you do that, the commitments are known, so it becomes a nice regression. So you don't really have to use all the complexity that I've shown you. And so this is what we are doing, and we have the time to do it because you can learn these problems every day as soon as you know the commitments. Because as I told you before, we have first the day out commitment, and then we have the problems that we have to run for the entire day. So once again, we are exploiting some of the structure of the application here to simplify the machine learning problem. And so this is what you get. You get an extremely high, accuracy when you start doing these things, as you can see. So you can learn these problems with, more than 99% accuracy, which is kind of remarkable in this particular context. So you could even think that you can use this prediction and actually seed an optimizer, and you would get the optimal solution extremely quickly. This is an interesting slide, which is telling you that if you try to predict use one machine model with the entire day, you can see that you are making a lot more mistakes. The accuracy is decreasing tremendously. You can actually predict typically these 4 hours in a row, but as soon as you do more, you start losing accuracy. And mostly this is because the commitments start changing dramatically. So this is, kind of what I wanted to say to you about the power system and these optimization proxies. You can also, one more thing that I needed to tell you is that, the time that it takes to train the single model is an order of magnitude longer than training the smaller models as well. So let me actually show you that the very similar techniques can be applied to scheduling problems, really discrete optimization problem. And so this is work that is published at AAAI with Nando and one of his students. And once again, there are 2 points that I want to make. The first one is that the network here, once again, is exploiting the structure of the application. So you see sub-networks here, which are machine layers and then job layers, because that's the structure of the optimization problem. Obviously, you have shell layers afterwards. And then what you see here on the right-hand side is, once again, the feasibility restoration, which also exploits the structure of the optimization problem. So once you predict the starting point of every job, you can actually put precedence constraints and start to optimize based on those precedence constraints. And in all the test cases that we had and that we tested, we could always recover feasibility using this particular optimization algorithm, which is a linear program. It may not always be possible to do that. The prediction can actually introduce a cycle. It never happened to us, but if that happens, you can actually also recover feasibility using a greedy algorithm, which is well known in scheduling theory as well. So the benefits here on some test cases is very substantial. The star that you see there is the behavior of the optimization proxy plus feasibility restoration, and you can see the optimality gap on the y-axis. And so in a very small amount of time, you actually typically are having a performance that it takes very long time for the state of the art, in this particular case the CP optimizer, to actually achieve the same quality. I will give you you can see the times that it takes for the CP optimizer to get close to that particular quality, and in sometimes it doesn't even get there in the within the time limits that we put. And so these are the results here in a more quantitative way. I think the two important things to see here is that compared to traditional heuristics that are extremely fast, the quality is an order of magnitude or 4 order of magnitudes larger. And you can see also the time that it takes for the state of the art to actually do better than the machine learning algorithm plus the feasibility restoration. So, completely different application, same methodology, and very similar results. So let me talk a little bit about learning to optimize snow. And so what we are going to do here is actually learning a component of an optimization algorithm with a machine learning model. And so this is an application in a ride-sharing system. What you see here is a ride-sharing system for serving all the taxi trips in New York City. So this is a centralized system. So you control all the drivers, and you can do ride sharing, and you try to minimize the waiting time of every one of the riders. The way we optimize this is basically by batching requests up to about 400 requests every 30 seconds, and then you optimize, and then you repeat the cycle. So it's a real-time optimization. It's somewhat myopic because you only batch for 30 seconds. You don't see what the future is going to be. I'm going to skip what we do for the optimization, but essentially we do a column generation. And the results are, very nice in general. So you can actually have a waiting time of, less than 4 minutes with 2,000 vehicles. To give you a sense, there are about 12,000 taxis serving this request in New York City. So I was really happy with this until I asked my students to actually visualize the vehicles which are idle. And then I was completely ashamed of what we were doing. So what you can see here is that the blue dots are actually the vehicles which are idle. They don't do anything. Because it's not cost effective to actually deploy them. They would increase the expected waiting time too much. And so these vehicles basically serve no purpose. Of course, over time, they move more to the center of the city, but it takes a long time to get there. So what we decided to do is to actually add a model predictive component here, and a relocation algorithm. It's also an optimization algorithm which relocate the vehicles every, let's say 5 minutes. So, this is happening at a lower frequency and also at a coarser granularity. But it's very important for maximizing the utilization of the vehicles. And so when you do that, you can see that some of the vehicles that you see on the right there, they are idle right now, but they are going to be dispatched in a couple of seconds. That's what the relocation algorithm is going to do. Look at all the idle vehicles and then relocate them to a place where the demand is located. You can see now that these vehicles are relocated to a center of the city here. And so when you do that, you have essentially 30% improvement in waiting time, which is kind of nice in this application as well. So I'm gonna go very fast on the way we do that, but this is a very complex MIP, and once again it has various kinds of physical constraints. You have the flow conservation on the vehicles and on the riders, and you minimize the number of riders that you cannot serve and the relocation cost. And this MIP is so hard that if you have a set of, let's say, 6 or 7 periods, you cannot solve it in a reasonable time. And so what did we do? Well, we basically said, well, we can solve it. It's just we cannot solve it in the real-time requirement. So let's learn it. And once again, the instances are very similar. We have a large amount of historical data. And so we learned this particular optimization problem. But the learning is actually very difficult because most of the demand is sparse on this particular problem. So the way we do this is we basically first aggregate the demand, then we learn, then we do feasibility restoration again, and then we disaggregate. And so, the only thing that we really need to learn is which vehicles have to be relocated from zone I to zone J in the first period. And since that's very often way too sparse, what we do is we simply predict the vehicle that are relocating from zone I and the vehicle which are relocating to zone J, for instance. And so once again, you use a deep learning network to do that. And then you disaggregate once again using a transportation model, trying to see which vehicles are going to go where based on the fact that the vehicles that have to leave and the vehicle that have to come in various zones. So once again, polynomial time to restore feasibility. And so what you see here is that the improvement is very interesting because now you can actually have model predictive control algorithm which reason about a much longer time horizon, which gives you very significant benefits. So this is, the model predictive control with 2 periods. This is with 6 periods. And you can see that the machine learning algorithm and the optimization algorithm are very close. So that's the benefit that you have there. You can have an optimization problem which takes too long, but when you learn it, you have learned it once, once for all, and therefore you can apply it in, in milliseconds. The interesting thing is, once again, we are building, digital twins for, these operations. And we now have essentially a policy for this particular, for this model predictive control. And since we have the digital twin, we can use that digital twin to actually improve that particular policy using reinforcement learning. And that's what we're doing here as well. So we use a policy gradient optimization to see if we can actually, improve the optimization proxy. And the way we do that is by generating a variety of trajectories using the digital twin, and then essentially doing policy gradients optimization. And the results are also interesting in the sense that they don't change the waiting time, but they decrease the relocation time, the relocation miles by about 8 to 10%. So this very simple policy gradient optimization there is allowing you to decrease your consumptions, your energy consumption by about 10%. So this was, learning to optimize, where I basically took one component of this big optimization system and replaced it by a machine learning algorithm, including, reinforcement learning. So what I'm going to move now is end-to-end learning, and this is a paper which is going to appear very soon. And the idea there is to, essentially do this end-to-end learning or end-to-end or decision-focused optimization. And as you know, the traditional way you combine forecasting and optimization typically is that you collect data, you do the prediction, and you use this prediction to make decision in optimization problem. But when you do that, fundamentally, you forget how, you don't take into account how the predictions are going to be used in downstream decision, in the downstream optimization algorithm. And in addition to that, typically the objectives of the prediction models are typically to maximize, accuracy. And that may not be really aligned with what you do in the optimization problem, which may be minimizing cost or maximizing profit or maximizing some kind of utility function. So this idea of end-to-end learning is to actually merge, the optimization problem inside the machine learning pipeline. And you view the optimization itself as a differentiable object on which you can do a gradient descent. And so, so there is a lot of work in that area in different community, in the OR community, in the AI community. These are some of the papers. We're going to use some results for the first one. They are, very complementary result by Bistra and her colleagues in other works. And this is also an interesting paper, which is more focused on continuous problems and not discrete problems. And so here, what I'm going to show you very quickly is how you can do that when you are trying to learn to rank. So what you have is that you have queries, you have a set of items that you can rank. Every one of them is a set of features. You are trying to protect some groups. You want to have a ranking which is fair. I will give you the definition in a moment. And then you obviously have the ground truth to actually predict, to actually give you what should be the scores of every one of these items. And so what you're trying to do is find a policy which maximizes the utility of your ranking. But we have also a fairness goal, which means that every one of the protected group have to have the same kind of visibility in the ranking, like the general set of items. What you do in practice is you try to bound the differences between these two, between, let's say, the general set of item and a protected group. And so what you do, once again, is you're going to, use a deep learning network for predicting the scores. And then these scores can be used in an optimization algorithm to find the ranking policy, which is a double stochastic matrix there, where, Pij is the probability that item J is in position G. And the interesting point is that you can put also these fairness constraints, which are bounding the difference between different groups and the general set of items. And so what we do when we do end-to-end learning is that we put everything inside the same pipeline. So this optimization model becomes a differentiable object. And there is this beautiful results by Adam and Paul, which tells you that you can actually do this, that you can have an approximation of the gradient by solving two optimization problems. And the results are quite spectacular in this on the traditional set of benchmarks, because not only you can guarantee that you satisfy these fairness constraints, but what you can see also is that you are actually having a much better utility than the traditional method, which use kind of a Lagrangian relaxation approach. And so once again, this is very interesting for a variety of applications. You can actually merge optimization and machine learning in one pipeline. So let me conclude by telling you about one other particular application area, which I find extremely useful, which is learning inverse optimization. And this is in the context of design, and especially the design of radio frequency circuits. So what people are using for 5G and 6G in the future. And so typically these circuits are using a lot of passive element because they can do a lot of different things. But the design of these passive elements is very, very difficult. So typically when a designer is designing those circuits, they basically specify the performance of these circuits that they want. But afterwards, what they have to do is to find the right physical parameters such that you get that performance. And the only way they can do that is by using simulation, which are extremely time consuming. So they will say, hey, with these physical parameters, what is the performance that I get? And then they look at the result and they say, that's not what I want. I'm going to change this a little bit. And then they continuously iterate until they find a solution which has the quality that they want. And so this is what typically they do. So they find the physical parameters, they look at the performance, and then they iterate. And it takes a very, very long time. And so what we do is essentially the opposite. We are saying, hey, what I want to do is that I want from the performance that I want to, the target performance, I want to derive these physical parameters. So the function f, basically I'm inverting it to actually finding, this is an inverse optimization that I'm trying to learn. And so in a sense, what I do is that I have all the properties that I want to achieve, and I'm learning this electrical, geometrical parameters that I need to have on my passive circuit. And so typically behind the scene, what you're using is once again, a residual network with many, many different layers. And the results, are, this is the accuracy, which is high, but the most interesting thing here is to show you how this actual learning system can be really, really close to the target performance that the designer wants. And so when you are this close to the target, it doesn't take very long for the designer to actually get the performance that they want. And so this is a big application area. This is a baby step. Obviously, this is only one device in isolation. But if we can enlarge this to the real, to the entire circuit that we are trying to design, this can be a game changer in the circuit design industry. So let me conclude now. I have about 2 minutes, I think. So what I try to tell you is that we have these different ways of combining machine learning and optimization. Optimization proxies, learning to optimize, end-to-end learning, and then learning inverse optimization. And they all have, really interesting applications in engineering. Some of the key insight that I wanted to tell you today is that we can transfer a lot of optimization theory into machine learning. Obviously, you have to adapt it, but this is one of the nice things that you can do. This predict and restore is becoming very prominent in this area. So you try to get very high quality prediction, and then you have an optimization algorithm which is dedicated to actually restore feasibility. And the other 2 points that I wanted to make is that both the prediction and the restoration phase are typically trying to exploit some of the structure of the application, such that you can learn more effectively and you can restore feasibility in a more effective way. So that's what I wanted to tell you, and I'll be very happy to answer any questions that you may have.
Hey, thank you very much, Pascal, for this really comprehensive talk spanning many topics. So we're now ready to take questions. So if you have one, please feel free to unmute your mic or type in the chat, and I can relay the question. So maybe I'll use my privilege here and start with one. So Pascal, I know you co-authored a book years ago on stochastic combinatorial optimization. And back then, deep neural nets were not all the rage that they are now. So I was wondering, would you say kind of your, if you were to rewrite some parts of that book in light of these results, do you think they would look different?
Interesting question. So first, I think this book is still very much the state of the art in many of these systems. So it's actually the techniques that we had there, this rolling horizon optimization is actually still the state of the art in many routing problems. So that's number one. This being said, I think what this machine learning algorithm would allow us to do, I believe, is to actually speed it up for applications where you have less time. So I think what we just did here on the ride sharing application, we could do that for this application as well. And what you would get is actually a much faster, you could scale to larger problems, and you could also optimize, you could also use techniques like what I've shown you, like relocation, use more sophisticated optimization techniques inside those algorithms. So I think I would use very much the same technique, but I would speed them up with machine learning and with some model predictive control that I would probably learn as well. So I would definitely add a couple of chapters, but I think I would still build the same methodology for the way to solve them, because I think this is still, I think what I like about optimization is that this is essentially telling you the best you can do. And so if you can learn the best you can do, you are in a very good place. And even if it takes too long to find the best thing, you can learn it and then use it in practice. And you are very close to actually doing a very good job. So that's what I think this combination of machine learning for me is so interesting.
Okay, great. So are there any questions from the audience?
Don't be shy.
Don't be shy, yes.
Yeah, don't be shy.
You have about 99 slides to pick a question from. Okay.
You counted them.
Okay, so
maybe
Nando, yes.
Yeah, maybe I'll ask a question. Pascal, thanks for the talk. So I wonder regarding the last part, I think also that's a really interesting aspect, quite unique. What do you think are the challenges for getting there? So you're saying, well, you talk about this invertible networks, this invertible function. So what do you think are the challenges that we need to meet as a community in order to get there?
So I think what you will have, I think the state of the art now is actually looking at mid-sized circuit and things like this. But when you start putting all the circuit together and then they start having different physical constraints, I think it becomes much more complicated. Now you're looking at different circuits at the same time, and I think that's much more challenging. And so I think you need to. I think currently the learning system is not including enough of these physical constraints. And so the big challenge is going to be, can you actually take those constraints into account? And then and they are going to be both discrete and continuous. And that's going to be essentially the big challenges that we are facing. So it's going to be really, really a big challenge. But this is a challenge where, I mean, we have some of the basic blocks to actually start to address them. But you have to understand that this is a problem which is extremely complex, right? So you have designers that are extremely experimented in actually designing that. So I think the other thing that you can do to get there is to actually learn what a good design is. And so I think there is also a process that you can do in actually learning how the designer are actually designing those circuits and what is the intuition for a good circuit. But at the same time, you also want to make sure that you explore things that they may not explore themselves, because they will have a tendency to actually reuse some of the design that they have. So I think it can be a very fertile engineering applications for these combinations of optimization, simulations, and machine learning. But it's not going to be solved in, for the next AAAI conference. So it's going to take a couple of years to actually get there. But it's one of the things that we should definitely do.
So if I can ask a follow-up question, what do you think is the role of data in that particular context?
It's easy to generate data. I think that's what I like about optimization as well. It's easy to generate data. You can just generate data, generate input data and then solve the optimization problem. On some of these, you can generate data and get some of the parameters of these devices as well. You can generate some configuration and then generate, kind of get data for them. Now, I think the one point which is a little bit more difficult is when you start putting displacement constraints. So that's a completely different story, because now you have to start placing that. And so that's where things get more complicated. But once again, I mean, if I used to teach a computer architecture, and the way people design those circuits, there is a lot of structure. And so I think they explore different types of things, but there is an underlying structure in how they design those circuits. They are not designed from scratch and in a completely arbitrary fashion, because they have to build them and they have to be reasonable to build.
Thank you.